All right, students, let's start with a question. Have you ever wondered how it's possible for just one single element, vanadium, to create this beautiful rainbow of colors in a solution? I mean, it can be green, it can be blue, or it can even be yellow. So how does this happen? Today, we are going to uncover the secret behind this fascinating chemical behavior.
So the answer to that question lies in our topic for today. We are going to dive into the general properties of the transition elements, which you also know as the D-block elements. These elements are the reason not just for that vanadium rainbow, but for many, many other unique chemical properties.
Now you might be thinking, sir, why should we care about this? And that's a very fair question. The thing is, these elements are, well, they're absolutely everywhere. They are the real workhorses of our industries, acting as catalysts in some of the most important processes. They are what create the brilliant, vibrant colors in paints and pigments. And get this, they are even inside our own bodies. Just think of the iron that's in the hemoglobin of your blood. So you see, understanding them is understanding a very big and important part of the world around us. So what is the big secret behind all their special properties? You might think it is something very, very complicated, but it's not. Actually, it all comes down to one single feature. The secret is, they're accessible and partially filled d orbitals. That is it! Just remember this phrase. This one single feature is the root cause of all their unique properties. To really understand what this means, let's compare two types of elements. Think of a main group element, for example, sodium. Sodium is like a worker who has only one fixed job title. It will always form the Na+ ion. It's very predictable, no surprises there. But now, let's look at a transition element, like iron. Iron is completely different. It's like a highly skilled worker, a multitasker, who can perform many different roles. It can exist as Fe2+ in some situations, and in other situations it can become Fe3+. You see? This flexibility is the main characteristic.
Okay, now for your exams, you must know the formal definition, so listen carefully. Transition elements are those elements that have partially filled d orbitals, either in their neutral atomic state or in their common ions. Now, I want you to underline this phrase in your mind, partially filled d orbitals. This is the master key to understanding this whole chapter.
And this brings me to a very common misunderstanding many students have. We often think that colored compounds in chemistry are something rare or special, but for transition metals, it is the complete opposite. For them, being colored is the normal thing. It's the rule. A colorless compound is actually the exception, and this is a direct result of those partially filled d orbitals we just spoke about.
To really help this idea of flexibility stick in your mind, let's use a very simple analogy. Just imagine a transition metal is like a multitasking, experienced chef working in a very busy kitchen. This chef isn't limited to doing just one job. And this table shows you exactly what I mean. See, a specialized worker, maybe someone who only washes dishes, is like a main group element, one fixed role. But an experienced chef? That's our transition metal. The chef's diverse skills are like the partially filled d orbitals. And the chef's ability to switch tasks, from chopping to cooking to plating, that is just like the variable oxidation states of a transition metal. Simple, no? So why is it so important to understand this concept of flexibility? Why are we focusing on it so much? Well, because it solves a huge puzzle in chemistry. Without this idea, we simply cannot explain why transition metals show such an amazing range of colors, why they have multiple oxidation states, and why they form so many complex compounds, while the main group elements do not.
Now, to see how this works at the atomic level, let's build a mental picture together. Let's leave the kitchen analogy for a moment, and I want you to imagine a molecular stage. This will help you visualize exactly what is happening inside a single atom of a transition metal.
Okay, so let's build this stage, step by step. First, the stage itself is the atom. Now, on this stage, there are 5 spotlights shining down. These 5 spotlights represent the 5 available d orbitals. The actors on this stage are the electrons. And the performance? The performance is the movement of these electron actors as they jump from one spotlight position to another. It is this movement, this jumping from one d orbital to another, that creates the color, the variable oxidation states, and all the other special properties.
Now, let's look at some visible proof of this performance. We'll go right back to the very first question I asked you. The amazing rainbow you see in vanadium solutions is not magic, it is direct, visible proof of our molecular stage concept in action.
See how it works? When vanadium is in the +3 oxidation state, it has a certain number of d electrons, our actors, and the solution is green. When we change its oxidation state to +4, the number of d electrons changes, the performance on the stage changes, and the color becomes blue. Change it again, and the color changes to yellow. You see, each color corresponds to a different d electron configuration.
This flexibility is also absolutely crucial for technology. Many of the most important industrial processes depend on transition metal catalysts. The Haber process, which makes ammonia for fertilizers, uses an iron catalyst. The catalytic converter in your car, which helps reduce pollution, uses platinum and palladium. And the hydrogenation of oils to make things like margarine uses nickel. All these metals work as catalysts because their flexible d orbitals can interact with other molecules and help them react more easily.
Now for a very important example that actually proves our main idea. You might think that since zinc is in the D block, its compounds should be colored. But as you can see, zinc sulfate is colorless. Why is that? Compare it to copper sulfate, which is famously blue. The difference is simple. Copper has partially filled d orbitals, which allows its electrons to absorb certain colors of light, creating the blue color we see. Zinc, on the other hand, has completely filled d orbitals. The stage is full. There are no empty spotlights for the actors to jump to. So, no performance, no color. This proves our point perfectly.
After all these examples and analogies, I want you to remember just one number: 1. There is one single underlying cause for all of these fascinating properties we have discussed.
And what is that single cause? It is the chemical flexibility that comes from having partially filled d orbitals. This one idea unlocks everything about transition metal chemistry. Their variable oxidation states, their color, their catalytic activity, it all comes from this one property of flexibility.
So for your final exam preparation, let's just recap the 3 most important points from this entire explainer. 1. The core idea is that partially filled d orbitals create chemical flexibility. 2. Your mental image should be the molecular stage with electron actors jumping between the d orbital spotlights. And 3. The key example to remember is the vanadium rainbow, which is visible proof of this flexibility in action. If you can just remember these 3 things, the core idea, the mental image, and that one key example, I promise you, this whole topic will feel much more manageable and much lighter in your exams. So, with this understanding, are you ready to go and master the D block?